Hi, this is Chris Jobling with another of the pre-session lectures. This one is on state space models and is part of the introduction to state space that I'm going to be doing in week 7. So, state space is a technique that is used in modern control theory. What we've been looking at so far in the course we could call classical control theory based on transfer functions. But these are limited in that they can only be used for systems that are linear time invariant and to some extent single input, single output as well. Whereas modern control systems theory is based on time domain description of systems, more specifically arrays, and these are a bit more flexible in what they can do. Because they have a nice matrix form, they're easy to simulate. They can be put into Matlab and new design algorithms, things can be developed. And everything we've learned so far also applies to state space, so we're not losing anything by going down this route. But state space is going to occupy us now for the rest of the course, and in the first couple of weeks we'll be introducing the topic, and then we'll look at how state space models are used in control system design towards the end of the session. Things we can do with state space models: we can handle multiple input, multiple output systems without too much difficulty. We can extend the ideas to systems where the coefficients are time varying. We can also look at things like controllability and observability, which are important concepts that we'll talk about later. We can look at powerful state compensation feedback methods such as state feedback, observers, linear quadratic regulators, and so on. And that leads us on to an optimal control theory and tools that allow us to get the best possible design for a given set of circumstances. So they're very powerful, and they lead to very powerful techniques. We can only scratch the surface on this course, as usual, a lot of these things, but hopefully allow enough of an introduction to be able to carry on should you need to find out more later on. As a sort of motivating example, I'm going to use this simple circuit where we've got a resistor, capacitor and an inductor in series with a source. Source is a current source in this particular case, and I want to develop the state equations from this model. So if we write down the equation for the elements in the circuit, we have one element which is due to the capacitor. So basically this is the current in the capacitor is equal to C times the voltage across the capacitor, derivative of the voltage across the capacitor. Then we've got another equation due to the voltage across the inductor, which is given by V equals L di by dt. So that's another equation. And we have a further equation which is the voltage across the resistor, which is just R times the current through the resistor. So those are fairly straightforward, and if you're not sure about the equations, if you just go back to the previous slide, you'll see how those equations come about. In addition to that, we've got the continuity equations, compatibility equations, and Kirchhoff's voltage and current laws. So the input to the system must equal the two currents in each of the branches of the circuit, and the voltage across the capacitor is equal to the voltage across the inductor and the voltage across the resistor, summed together. So with those equations we've got enough information to be able to construct a state space model. We like in our case to, rather than use derivatives directly, to use the integral. So we will be looking for equations where we are integrating the derivative to find the actual voltage. So this is the capacitive voltage, this is the current through the inductor. So we'll use those two equations, and with all that taken into account, we can build up some block diagram components representing those equations. So this one represents the voltage through the capacitor. This is the resistance, the current through the resistance. This is the current through the inductor, and the voltage across the inductor. You can see the inputs and outputs of those things, and then we have the compatibility equation equations here and here, one for current, one for the voltage. And there's really only one way to wire this up, and that's this one here. So putting all those equations together, we have two blocks which involve an integrator. This is for the voltage across the capacitor, this is for the current through the inductor. We have a bit of feedback through the resistor around this circuit, and we have overall feedback from the current through to back here to provide the current going into the capacitor. So that's the block diagram representing the state equations that we're going to use in a minute. To write down the equations for that, we look for equations where we've got the derivative on the left hand side. So this is the derivative of the capacitive voltage across the capacitor, derivative of the current through the inductor. By definition, that's 1 over c times I2, but we also only want to involve variables in these equations that are so-called state equations. So we only want I1 and V31 to actually appear in the equations that we're going to derive here, for reasons I'll explain in a minute. So instead of I2, we replace I2 by its compatibility equation result, and that gives us minus 1 over c times I1 plus 1 over c times u, where u is the input to the system. And we've got another equation, di by dt, that's 1 over L times V32, and again, because we don't want V32 to appear, we want to eliminate it, we replace it by its equivalent through the other voltages, so 1 over L V31 minus R over L times I1. That gives us the equation, and you'll notice that only V31 and I1 and the input appear in these equations. That's quite important, a feature of this model. We can then put these equations into vector form. So because we've got equations, two essentially equations, V31 and I1 and u, we can write the differential equations in a matrix form like this. This is easy to see that these two are equivalent. And we call this vector here, V31 I1, we call that the state vector. So that there is a state vector, this is the derivative of the state vector, and that's the sort of format we get for the general system, and this is the system input to the system. So having done that, we can generalize a bit further by replacing V31 and I1 by just sort of anonymous variables, x1 and x2. So x1 is V31 and x2 is I1, and then x1 dot is the derivative of x1 and x2 dot is the derivative of x2. The other equations don't change. And so in general, we can do this with any differential equation. Any nth order differential equation is going to have this format. There's going to be the highest differential on the left, and then some function of all the other differential terms from the n-1th down to the 0th derivative, plus the input, plus t. So these could be time-varying equations. So we have a function, general function like this, and that can be used to generate the state space models. So in general, the simplest way to do this is to just define x1 to be y. So the derivative of x1 is dy by dt, which is x2, and the derivative of x2 is d2y by dt squared is equal to x3, and so on, down to this one, dx to the n minus 1 is dn minus 1 by dt n minus 1 is equal to xn, and then the final equation, dxn by dt, or xn dot, is the actual function, the original function. So we can always convert any general nth order differential equation into this general state space format. And we're not saying anything about the nature of f in this slide, although in the examples that we'll be looking at, f is a simple matrix of coefficients. So here's a second example. The differential equation d2y by dt squared plus 3dy by dt plus 2y equals u. We want to convert that into state equations, basically using the previous result, I'm not going to give you the example in these slides. We'll do the solution in the live class, but it's not very difficult, so maybe you would like to try it before class if you can. So that's a general state equation. In a lot of the sort of systems we deal with as control engineers, we're dealing with physical systems, electrical, mechanical, aerospace, chemical and so on, and therefore some of the states that we're dealing with will actually be physical variables, things like charge or voltage or current in electrical case, or force, velocity, mass and so on in mechanical systems. So often the models we come up with when we're coming up with state equations are based on the physical intuition we have about the system we're controlling. In other cases we may not know very much about the system, but we can measure its input-output behavior, in which case we might try and fit a sort of general state equation to some measurements. But often if we've got the physical states, we can utilize that. Certainly if the equations of motion are sufficiently simple, we can utilize our knowledge to create physical state variables. And the thing about physical state variables is that they are where the energy is stored in the system. So current, voltage and so on, they're clearly points at which energy is stored, and so the rate of change of that energy is an important quantity. So just to illustrate that, we've got a third example. This one we looked at very early in the course, so you might want to revise the notes for one of the first lectures. It's a spring mass damper system. We've got a force applied to a mass. We're interested in the behavior of X, and we've got a resisting spring and a resisting damping pot with these equations. So you might like to try and come up with the state equations for this model as well, although again we will do the example in the lecture, in the actual session. Some properties of state equations. We can usually solve the equations for any given input and initial conditions. So we can basically solve the differential equations. If we have other variables in the system, we can determine them from the state solutions and the equations that we used for the output. Physical states are associated with energy storage, I've already said. Another thing about state equations is they basically encode the system's whole past history. So once the system is running, the states basically have memory of everything that happened to that system over all the time. But another important point is that the choice of states is not unique. In physical state variables, obviously there's some choice, but you don't have to label them necessarily the same way. Different orders are possible, but also you could come up with equations which had nothing to do with the physical variables in the system at all. And so there's no unique state equation for a particular given system. For linear systems, which are what concern us most on this course, we can use control methods that work quite well. If we have a nonlinear system, we can often linearize the system around a given operating point to allow us to use linear methods. This is essentially what's happening when you do linmod, or you use a linearization tool in Simulink. It's basically looking for equations of motion around an operating point. We can use linear models in matrix equations, so they can go into Matlab and sophisticated algorithms can be developed. Linear time varying systems of matrix elements which are functions of time, but we can also cope with those. Time invariant systems have constant matrix elements. So let's look at the general state equations. We basically start with a state vector. So the state vectors here are the variables we use in transpose operator, because this is actually a column vector. Derivative is simply the dx by dt, and for shorthand we use that, call x1 dot and x2 dot and so on. There can be any number of inputs to a system, so we represent that as again by a column vector of inputs, and there'll typically be n states and q inputs. So in general we're going to get a set of equations like this for a linear case. X dot is equal to some matrix with coefficients x, a, 1, 2 and so on, where these are multiplying by this vector to give us the state equations, and then similarly b, 1, 1 through to b1q times u and so on. So again, matrix times a matrix, matrix times a vector, and a matrix times a vector. And we can write that more succinctly as just x dot equals ax plus bu, where a is this vector here, and b is this vector here. We can also think about the output equations. So for illustrative purposes, these are all the outputs that we could get out of the circuit we used in example 1. So this is the voltage across the capacitor, this is the voltage, the current through the inductor. Those are the states that we've already defined, so they're just one times the state variable. And then we've got some combinations. So V32 is V31 minus R times I1, and V21 is R times I1, and I2 is U minus I1. So those equations are there. We could write them all down, and we can have again put them into a vector form. All the outputs we're interested in, the state variables V31 and I1 plus the input U, and this matrix here has got all the possible other equations we might be interested in to find out the variables in the system. So we define a general output vector y, and this time there'll be r of them, and we can then write an equation, a general output equation relating y to the states plus the inputs. And so we have a big matrix C of all the coefficients for the states, all the combination of the states that go to make up y, and then a similar matrix for all the combinations of u that make up this term here. And in general we've got y equals cx plus du. And then again, C is n by r, called an output matrix, d is r by q, and called a feed-forward matrix. So the full state space model, taking into account possible outputs we might be interested in, is this: x dot is equal to ax plus bu, that's the state equation, and then y equals cx plus du is the output equation. So this set of 4 matrices basically represents the system that we want to build. If the system has physical reliable states, it's called proper, and if D is null, in other words there's nothing in the D matrix at all, it's empty or 0, then the system is called strictly proper. And if we wanted to think of a block diagram, this is what we'd actually put together. This is a vector diagram, so when you see this block here with an integrator in it, it's not a single integrator, it's a set of integrators in parallel feeding x dot into x, and then x is fed into the A matrix to give us the output here, u is fed into b, so these two are added together to produce x dot, so that's the x dot equals ax plus bu equation. And then the output equation, this matrix takes the states, combines them in a way that is relevant to the system, and then we've got a similar matrix which feeds forward the u inputs to the output. So this y is cx plus du. And just to sort of close out, this is the state equation then of the example we started with. It's been extended a little bit because we've got all the outputs that we possibly could have listed as well. And I'll show you that in Matlab in a minute. And this is how we might define that in Matlab itself. So we can use Simulink and linearize, or we can define state space matrix directly in Matlab. These are the equations representing the capacitor inductance resistance, the ABC. This is the C matrix where all the possible outputs of interest are listed. And then we've got a state space model, takes the A, B, C, D matrices and produces a linear LTI block, as it's called in Matlab, called circ SS in this case. And we've got additional tools on this function, so we can define the state variables, give them names, name the inputs and outputs and so on. And then we've got values that we can do for that. So before we move sort of to a conclusion, let me just show you one or two things. This is the block diagram of the model that we derived for the first example in Simulink. This is the more complicated example where all the possible outputs are listed here, all the various voltages and currents that are in that circuit. And it looks a bit more messy because of the way we've had to combine things differently. In the original system we're only concerned with, I think, this voltage and this current, but now we've got all these others as well that we need to take account of. So additional components to allow us to measure those various and combine those various variables. And then here is a model where we define the system. So here is setting up the parameters. I'm just using 10 microfarads and so on. So we define the ABCD matrix, these are state variables, and then we produce a step response. So if I execute that, sorry, I need to execute this first to set up the variables, and I can execute that. We go to the other window in Matlab, and we can examine the A matrix. Or rather, sorry, the circ SS matrix. We can see if we do circ SS in the command window, we get a fully documented model with all the voltages and currents labelled in the inputs and outputs, so that's quite nice. We can do things like step of circ SS to get the step response. And it shows you all the variables, so all the voltages, all the currents listed there, and so on. And so we've got other things in this. We've got a version where we can generate the model from the Simulink using what's called linmod. And we can do a run on that. And then we can run linmod, this linearization to plot the results. So you can have a play with that when you get a chance to later. So that's the models in Matlab. Just to conclude then, this ends a sort of pre-class session, but what I will do in the actual lecture, in addition to the examples that I've already sort of put up on the slides, I would like to just have a look at the state space model for the antenna azimuth case study from NICE, so we can sort of show how we could apply what we've learnt to model the case study problem as a state space model. So that's what we'll do in the class. We'll do the examples on that case study, and hopefully that will be useful to you, and we'll see you in class in a few days' time. Thanks very much.